Okay, so I guess we'll get started on this last section in Chapter 7. So Chapter 7's been all about model selection, picking our things. So just there's a word of caution that our book gives us, and that says, the coefficient estimates of parameters will often be too large after a process of variable selection. Okay, and that also means the corresponding p-values of these coefficient estimates will also be too small. Okay, and so the idea is, you might have some response y that depends on multiple variables, but some of these variables might be very highly related, and if you pick one, then the other one becomes statistically insignificant. So what happens is that the variation due to, you've got x1 and you got x2, the variation due to x2 might get dropped out, might be deemed insignificant, and so the variation that was originally due to x2 kind of gets folded into the coefficient estimate for variable x1. So here's just a simple example, or a toy example. Just we might think of the price of a house could depend on the square footage of the house, so how much area is in the house, and the number of bedrooms in the house. Okay. But obviously those two things are going to be highly related, right? So if you see more square feet, or if you have more bedrooms, you're going to have more square feet, and vice versa. And so, when you do the analysis, it might show that only square foot is statistically significant, and the number of bedrooms is not. Okay, but I would think it's incorrect to say that the price of a house depends only on square feet and doesn't depend on number of rooms at all. Okay, but the variation that was due to number of rooms will then get folded into the square foot, and so the coefficients and the p-values will then make square footage appear even more significant than it actually is. And so that could happen when you're doing variable selection, okay? Versus a fixed model where you're just trying to estimate the impact of, how much does square foot affect the cost of a house, and how much does the number of bedrooms affect the cost of a house. Those things, if you say, if you keep those in a fixed model, saying these variables are important, we've got to keep them in there, then you'll get different estimates, but it might turn out that one of them's not significant. And so there's kind of this, it's hard, okay? You just have to keep that in mind when you're doing inference at the end of variable selection. Okay, and so here's, we're going to go through an example here, and it's a good example in that it shows that data analysis and regression can be difficult, especially when you have smaller data sets, and just these are some of the difficulties that you might encounter. Okay, and so the idea here is we're going to split our entire data set. So we've got a lot of data, and we're going to just randomly split it into two parts. We have the training data set and the test data set. Okay, and so we fit a model to the training data set. So this is, kind of like when you talk about machine learning, you've got supervised learning, and so regression is maybe the most basic form of supervised learning. You've got, what the output y's are, and you've got your input x's, and you're trying to figure out a relationship between the inputs x and the outputs y. Okay, And so you do that with the training data set. You fit your model on the training data set, and then you try to test out the same model. So at the end of the training data set, you pick a model, and at the end of that, you test out that model on the test data set, and you see how it performs. And hopefully, the model is still a good fit on the test data set. And so we'll look at that. Okay, and so what the data that we're looking at is we're going to look at this prostate cancer data set, the response variable that we're looking at is the log of the cancer volume. Okay, so apparently somehow we're measuring the volume of the cancer in the prostate, and we're looking at a whole bunch of different things. So we're looking at the weight of the prostate, the log of the benign prostatic hyperplasia, the seminal vesicle invasion. I don't know, all of these things, right? I have no idea what these are. Well, okay, Gleason score is apparently something that's related to prostate health and all of this stuff. This is stuff that I guess men have to worry about when they turn over 40 or something, right? Get your, I think that, I don't know, whatever. Okay. So it's already split into two parts: the training data and the test data on the book website. So we're going to download the training data, and we load that up, and we'll just create a plot here. Maybe I can get a bigger version. So we'll zoom in. Okay, so this is the entire all of the things in the pairwise. So we'll look at this is a response of cancer volume, and we want to see how this relates to all of these things. And it seems for the most part like we don't see a whole lot of curvature in any of these single variables. You know, we have some cases where like you've got a whole bunch of measurements at one particular value, whatever it is, negative something, and so you have, and then you got this dichotomous response, and you got a few oddities here, but as far as any one of these things showing curvature, it doesn't seem like that's the case at this point in time. So so we'll just try fitting the full model. Okay. So the full model is just, all right, I'm sorry. We're looking at, I guess we're looking at LPSA. I don't know, I'm confused. But we're gonna fit the full model where we're predicting LPSA based on all of these other things. Okay. And we'll create the standardized residual plots. And so here, I'm just going to create a bunch of these. So this is the standardized residual plot versus cancer volume. No pattern there, that's a good sign. Versus log of the weight, also no pattern, so that's good. This seems okay. All right, and so just kind of flipping through all of these, we're not really seeing a whole lot of pattern in terms of the standardized residuals versus any of these predictors. Okay, and we can plot the fitted values versus the standardized residuals, and again we see no pattern here. So all of this is a good sign in terms of, is our full model, does it do a decent job of fitting the data? Okay. And we'll look at the fitted values versus our response. Okay. And this looks to seem like it's got a fairly linear relationship, and we can fit the the fitted line from our model, and that looks it looks decent. Okay, so again it's nice. Okay, and you know, we got it. This is a textbook example here, so of course a lot of these things will behave nicely. Okay, and we can look at the diagnostic plots. Okay, and again, as we flip through all of these, they all have nice behaviors. Okay, so that's a good sign. Our normal QQ plot, you know, we got a few things that deviate, but overall a good fit. Okay, maybe a little bit of a sign of some decreasing variation in our residuals, but it's not entirely worrisome. Okay, it does seem to go down a little bit, but we're not too worried. And then looking at the residuals versus leverage, we can add a kind of a using our 2 times the number of predictors over the data points that we have as a guide for what has high leverage. These data points might have high leverage, but they don't seem to be bad leverage points. So all of these things are good signs as far as the model that we have. Okay. And then again, just performing even more diagnostic plots, looking, we can look at marginal model plots for each of the predictors. Oops. Okay, so the marginal model plot between the dotted line is here. I'll turn key on to true here. So the dotted line is the fit according to our model, and then the blue line is based on just the lowest regression. Okay, so of course the idea is we want these two to match as closely as possible, and this seems to indicate that they do. Okay. So over here, also a good match, with the exception of this kind of down here, just because we got one data point out there. Another seems pretty good. So looking at all of these marginal model plots, it appears that the model fits the data quite well. Okay. And the fitted values versus the response. This is kind of the most telling of them. So the model is the dotted red line, and according to our data, this is the lowest fit, and that seems to be in agreement. Okay, so everything looks good. All right, and so we can look at the coefficients and our selection, which variables are significant and which ones we should keep and whatnot. Okay, so when we look at this, it seems like a few of these things like Gleason and age are not significant, and so we can go through the process of doing an exhaustive search or stepwise selection to try to get the subset of variables that we want to keep in our model. All right, we can see if there's problems with multicollinearity by doing the variance inflation factor, and when we do that check, none of these are over 5, so it appears that multicollinearity is not a serious issue going on here. Okay, and then we produce a whole bunch of added variable plots. This is kind of what our book advocates for us to do. And so, I'll plot all these, and it seems we'll see some of these appear significant, Okay. This is an interesting one. When we look at the log weight, most of the data actually seems like there's not a whole lot of relationship, but I think this one data point out here ends up pulling our entire line up that way. Okay. Over here also not a whole lot. Maybe these data points are quite influential, but when we looked at the as far as the p-values go, this one doesn't seem to be very significant anyway. Okay, and so all of these, we can kind of get an idea of how they vary. And so just throwing all of these out, this one seems to be quite flat and not significant. And apparently that's the fit there. Okay. So just looking at this one data point, we can label it, and we can have the added variable plot identify certain numbers. So we just want to identify the one with the largest R, and that would be this one here. Okay. And in some of the other plots, we can kind of pick out the ones with like the largest X or the largest Y or whatever it might be. So this is, we're going to see later on that this data point causes problems for us. Okay. But we'll perform the exhaustive search for variable selection. Okay, so we're going to do that. We create a matrix with all of our predictor variables. Okay, so this is all of our predictor variables right here, and then we load the leaps package, and we run the command regression subsets. Okay, and it worked through it quickly, and we can just ask, what did you find, right? And so it did exhaustive search for subsets up to size 8, and it says, if you want to keep just one variable, then the one you want to keep is cancer volume, and if you want to keep 2, these are the ones you want to keep, so on and so forth. So we can plot how the adjusted R squared changes as we increase the number of factors. Okay, and so it seems like it keeps increasing. The jump from 4 to 5 is not significant, but it seems like it maxes out as far as adjusted R squared goes. It maxes out when we include 7 factors, and the addition of the 8th one decreases our adjusted R squared. Okay, there's the function subsets, which kind of labels which variables we would have kept for each of these things. And we can create a giant table of every single one of these models, right? So keeping in mind the models that the exhaustive search recommended, we're going to create the model using just 1 predictor, 2 predictors, 3 predictors, 4 predictors, 5, 6, 7, and the full model with all 8 predictors. Okay, so the selection of variables for each of these was determined by the output of the exhaustive search algorithm. Okay, and so with this, we're going to do a whole bunch of calculations here. And this is kind of the tedious part. We're going to calculate the AIC for one model, the adjusted AIC or the corrected AIC for the model with one predictor, and the BIC for the model with 1 predictor. Okay, and then so I'm going to run through this and calculate each of those three statistics, AIC, corrected AIC, and BIC for the models with 1, 2, 3, all the way up to 8 predictors. Oops, I messed something up. Oh, no, that's not code to be run. All right, and so I've created a table that includes all of these together. And I hope it runs. So after doing all of those calculations, here it is. Okay, so we can look at the adjusted R squared, and I've gone ahead and I've highlighted the largest or the lowest values that we have. So adjusted R squared maxes out when we have 7 predictors. AIC maxes out when we also have 7 predictors. The corrected AIC maxes out with 4 predictors, and the BIC maxes out with 2 predictors. Okay, or not maxes, but minimizes, or is most negative for these situations. So we've got kind of like 3 competing models, and we have to make a decision. All right, so we'll take a look at each of these models. So we look at the model with just 2 predictors, which was cancer volume plus weight, the logs of those. The model with 4 predictors, which were these 4, and the model with 7, which were these 7 predictors. Okay, so we look at the model with 2 predictors, and both predictors turn out to be significant. Okay, the cancer volume and the weight, they have these p-values. So those are both very small. That's what we have. With 4 predictors, we have cancer volume being significant at the 1,000th level, weight and SVI being significant at the 5% level, and log of BPH being significant at the 10% level. It's almost at 5%. Okay. And then with 7 predictors, this is what we see. Okay, and so we get this one. So a lot of these are significant. This one is not significant. Age is not significant, but it gets included with 7 predictors. And then LCP is significant at at the 10% level. It's around 6.5%. Okay, so I don't know. What do you guys feel in terms of the model that we should use?
Maybe decrease the parameters.
Okay, so 7, 4, or 2. What do you think?
I haven't looked at 4 and 2.
We did. So the 4 and the 2. Yeah. Okay. So the thing to keep in mind. Well, we'll have to. It seems, because we know that these parameter estimates are inflated when you do variable selection, it might seem like this one, even though it's almost significant at the 5% level, maybe it's not all that significant. So maybe it appears that the model with 2 parameters is the preferable one, but it's hard to say. It's hard to say. Okay, so we have 3 competing models, and this is where we do the testing part. Okay, so we use the training data set, and we found kind of 3 models that seem to be good, maybe with a preference towards the one with two predictors, or 4, and to make our decision here. Okay, if we look at the the F on all of these are very very significant in all three cases. Okay.
Question.
Yes.
The more predictions you add, the F statistic is only going to get more significant, right?
Not necessarily, because your denominator degrees of freedom changes. Your numerator and denominator degrees of freedom will change, and so here with 4 predictors, our F statistic is like 30, and it has a p-value on the order of e to the negative 14. And with 7 predictors, our F statistic is only 19, with a p-value on the order of e to the negative 13. So it is possible that the F gets weaker as you add more parameters, but that in of itself is not the judge of which model is better. It's just, is your model significantly different from no prediction? And yes, the answer is yes. Okay. That's all we can really say with the F. We can just say, is our model significantly different from just predicting the mean? Okay, so we have, we're going to load up the test data, and we're going to see how our models perform on the test data. Okay. So we'll do that. We'll load up our test data. Okay, so we're going to fit the model with 2 predictors, and we'll ask for the summary here. Excuse me. Thanks. Okay, and what do we see? Cancer volume's significant. Log weight, not significant. It's a bit of a disappointment. Okay, we'll look at the model with 4 predictors. Okay, and recall that on our training data, these, they were all significant. These 3 at the 5% or less. And this one was significant at the 10% level. But when we look at it here, cancer volume is significant, weight is not, LBPH is not either. SVI remains significant, or is now even more significant here. Okay, and then lastly, we'll look at the model with 7 predictors. And only cancer volume is significant here. Okay, so in all of our cases, in all 3 of our models performed poorly with the testing data, and this is the hard part of regression and data analysis, is that you have your data, okay, and you can split it into training or testing, or you could take the whole data, but the thing is when you fit models, you're trying to find patterns in the data. And sometimes those patterns that exist are just flukes of this data set. And there's no way of knowing whether it's a real pattern that exists in the population or if it's just a funny thing that happens in your data. And maybe you can look into one individual data point or something like that, and then figure something out and make a decision that way. But usually, you just don't know. You don't know if the patterns you're picking up in your model are real, or if they're flukes. Okay, and so it appears that even when we went down to 2 parameters, our model was picking up something that was a little bit of a fluke. Okay, and so log weight turned out to be significant in all of our in all of our models, but it was probably a result of the fact that we had that case 45, right? That one. So let me pull up the added variable plots. So let me, I gotta attach the training data. We got our full model, and we'll look at this added variable plot. Okay, so if we look at this, it seems like this one, you know, high leverage, large residuals, so this would be a, quote, bad leverage point. So this one could be artificially making our variable log weight significant, okay? And so it is, sometimes it's important that we kind of just look at each of these plots to just see, are there certain data points that are influential and could be throwing off our analysis, okay? Yes?
So you're saying that, say we look at this data set and then we come up with this model and it just might totally not work with another data set, right?
Yes.
Does the number of observations affect how accurate our models are? As in, as the samples, or as the number of observations get larger, we should be more certain, right?
Yeah, okay, so the question is, do the number of observations influence how good our model is? Yeah. And the answer is yes. More observations, you are less likely to be susceptible to these random fluke type things, okay? Because, you know, if we had a lot more observations, we might have a large data point down here to kind of counteract what's going on up here, or, you know, with more observations, this thing by itself may not be as influential, type of thing. And so, yeah, more data is always better. You know, more data generally means your sample is going to look more like your population. You can kind of be more confident in that, but that luxury may not always be available. So it's hard. It's hard. Data.
Is there a guideline to avoid this happening?
Okay, so we have. Yeah, I don't know if we'll get to it. There's what we call robust regression methods, which try to avoid these types of situations, and you know, any way you split it, so if we take our full data set, we can split it into training and testing data, okay? And we can try to fit different models. And but the thing is at the end of the day, everything's still based on this one sample that we have. And so you can kind of try out, you might fit a model that works for all training and testing things that you pick out in this data set. But of course it's going to fit well because this is the data set that you have. So yeah. This is the challenge of statistics, which is always you're trying to make conclusions about the population based on limited data that you have, and you're always going to run the risk of detecting some kind of pattern fluke thing in your data. Okay, so we can do something that's a little bit dangerous, which is just throw away data point 45. Okay, you know, I don't have any information on this, but we can throw it away and just not to say that this is now the model that we're going to use, but we can kind of just see how this changes things. Okay, how important is this? Okay, so again, we should never get in the habit of just saying, oh, this data point is inconvenient, so let's throw it away. But it might be useful to throw it away and see how everything changes. Okay, so we have, what was this? Okay, so this was everything when we did that. So in this case, so I've thrown away data point 45 from all of our predictors. We combine them all into one matrix, and then we run the regression subsets. This is the exhaustive search on this on the data where we've thrown it away. Okay, so we can ask, what does this look like? Okay, and so now we see cancer volume is still the one that's significant in all of these, but if you're going to pick 2, the one that we now use is LBPH1 and things like that. I didn't go through the entire process, but we could go through and we can see. All right, so according to adjusted R squared, it seems like the model with 7 seems to be best. We can look at, I think, RS. We can plot the BIC. All right, and so it seems with BIC, it seems a model with 3 predictors is the best here. We can fit. So we've updated our model. This is one way to update the model, is you can just say update it with this subset, or you can just say, you know, create a model for whatnot. So this is with using the full model with data point 45 removed, and we can kind of get an idea of, you know, how everything has changed. And so now we see the weight is no longer significant. Okay, and we can look at AV plots of M2. And so here, this is all of them together. Okay, and so, you know, we got rid of that highly influential point for weight, and so we see that it's, you know, we still have an upward slope here, but it's not as influenced as when we had it like this. Okay, so comparing, oh, I guess when you change it down here, it changes in both spots. So we got rid of this point, and so the added variable plot for all of the variables look like this now. Okay, so you know, are there any other points that are potentially dangerous? I'm looking. It doesn't seem like it right now. And so we can, you know, looking at this, we can say, all right, well, according to BIC, we should have fit the one with 3 parameters, which would have been cancer volume, LBPH, and SVI1. So we can try our subsetted model. So let me just call this MO3, and this will be a linear model between what did I rename these things? So LSPA. Oh, I never updated it, did I? Okay, sorry, I should do LPSA1 is now LPSA without removing that data point. Okay, so LPSA1 as cancer volume 1, and I forgot what the other variables were for our selection of a model with 3. We want LBPH and SVI. LBPH1 plus SVI1. Okay, and we can ask, what does this thing look like? Okay, and so, you know, with our subsetted model, you know, now that we got rid of that data point, we have this. And so we can see, you know, how does this fit on our training testing data? Okay. So we'll attach prostate test, and we'll basically do the same thing. I don't know, we'll call this MO3 with the test. I want these, but of course the testing data doesn't have the. We didn't remove anything here, and we can just see kind of how it performs also. Okay, so I mean, here's, you know, it looks. So looking at this and this seems to kind of improve the. Wait, are these exactly the same? Did I mess something up? Huh?
Did you type M0?
Oh, I typed something in wrong. I'm like, this doesn't look right. Oh, M03. Okay, yeah, of course. Alright, so okay, let's see. Okay, and so in this case, this one turns out to be not significant at all. So maybe we have some problems here. Okay, so we can try to investigate, you know, what's going on. So if we look at what were we doing? So let me just. I forgot what I was doing here. We can create a plot where we are, this is log weight, and this is so these are the data points that exist for log weight in our training data and in our testing data. Okay, and so with the training data, because of that influential point that that appeared somewhere, the regression line was quite high. And in our testing data, it seems like this data point out here pulls it down, you know, kind of in the opposite way. If we fit the full model on the testing data, and we just kind of look at the relationship, this is not something. This is the one I wanted. LBPH. No. Okay. Okay. Now I'm not quite sure what I was saying, but when we fit our testing data to our model, what could end up happening is that just certain data points that randomly appear in either the training set or the testing set could throw off everything. Okay, so yeah, moral of the story, it can be hard. All right, we just have to be cautious, and you know, even if you get an excellent fitting model, right, you go through you get your data and it turns out to be awesome, and you're like, oh, all right, this is great, and then you try it out on new data and its performance totally sucks, right? Not necessarily your fault. It could just be the data that you had had a few random flukes that your model picked up on and you thought was real, and there's no way to know what is real and what isn't. I guess that's the sad reality of our jobs. There is a very good kind of this flow chart of what you should do in terms of fitting a model, and it's a good guideline. So I would say print this page out, and as you're trying to fit models in the future, just kind of follow the these guidelines along the way and ask your questions. You know, am I making good choices along the way? Okay. Have a good weekend, I guess. Is the homework going okay? Have you guys looked at it at all? No? Okay. Well, try it out. And okay, well, you got this weekend, all right? I mean, it's due Wednesday, so you should probably get started before Tuesday. And, you know, well, anyway, have a good weekend, you guys. So we'll see you guys on Monday.